In Lesson 7.1, we're studying geometric mean. You'll find the geometric mean between two numbers and solve problems involving relationships between parts of a right triangle and the altitude to its hypotenuse. How can geometric mean be used to view paintings? When you look at a painting, you should stand at a distance that allows you to see all the details in the painting. The distance that creates the best view is the geometric mean of the distance from the top of the painting to the eye level and the distance from the bottom of the painting to eye level. I'm going to take the time to do that next time I look at a painting. We should probably start off defining geometric mean. The geometric mean between two numbers is the positive square root of their product. Here's a more formal definition. For two positive numbers a and b, the geometric mean is the positive number x where the proportion a is to x as x is to b is true. This proportion can be written using fractions, a is to x as x is to b, or with cross products as x squared equals ab, the product of the mean extremes equals the product of the means. Or if you solve that for x, it'd be x equals the square root of ab. And here they write that out in the equation x squared equals ab. The two x's in x squared represent the means, and a and b represents the extremes of the proportion. So if they ask us to find the geometric mean between 2 and 50, we've got 2 is to x as x is to 50. So when we do the cross products, x squared equals 100. So x equals the square root of 100, which is 10. So to find the geometric mean between 25 and 7, we're going to write 25 is to x as x is to 7. And do our cross product. So we have x squared equals 25 times 7 is 175. And we're going to take the square root of both sides. And remember, when we simplify radicals, we could rewrite that 175 as square root of 25 times square root of 7. Square root of 25 is 5. We're stuck with the square root of 7 unless we approximate using a calculator. There's my terrible approximation symbol there. And going to the nearest tenth would be 13.2. Our first theorem of the lesson, Theorem 7.1, says if an altitude is drawn from the vertex of the right angle of a triangle to its hypotenuse, then the two triangles form are similar to the given triangle and to each other. So we're creating really three similar triangles. And I thought if we drew the triangles separately, it might be easier to see how they're related. If we mark angle x with one arc and angle z with two, and this makes a right triangle, so then this guy would also have one arc, and because there's only 180 degrees in a triangle, that guy's going to have 2, and we said z had 2, so then y up here would have 1. So you can kind of see with their similarity statement how they're all related. By Theorem 7.1, since triangle XWY is similar to triangle YWZ, the corresponding sides are proportional. So XW is to YW as YWY is to WZ. Notice that XW and ZW are segments of the hypotenuse of the largest triangle. So there's XW in the big triangle and ZW in the big triangle. The measure of an altitude drawn from the vertex of the right angle of a right triangle to its hypotenuse is the geometric mean between the measures of the two segments of the hypotenuse. So in this one, YW is the geometric mean of XW and XZ. So I'm adding variables to here so we can have something to hang a hat on. So our definition of geometric mean, we'd say x equals the square root of AB. In triangle ABC, BD is 6. They didn't give us much room on the diagram for that one. AD is 27. They want us to find CD. So all we have to do to find x is take the square root of 6 times 27. So the square root of 6 times 27 is 162. Could be rewritten as square root of 81, square root of 2, and the square root of 81 we know is 9. Or if we use the approximation button on our calculator, we get 12.7 to the nearest tenth. Miss Owlspatch is constructing a kite for her son. She has to arrange perpendicular two support rods, the shorter of which is 27 inches long. If she has to place a short rod 7.25 inches from one end of the long rod in order to form two right triangles with the fabric. What is the length of the long rod? Okay, I'm going to say it right here. If you were doing this problem, you would measure it with a ruler. But anyway, mathematicians aren't that way. So a more useful diagram, if we just cut this guy in half, there's our 7.25. Half of 27 is 13.5. Okay, so the proportion we can set up, WX, which is 2 arc angle to right angle, is to YX, which is 1 arc angle to right angle, as YX, which is 2 arc again to right angle, is to ZX. And ZX had the 1 arc marked angle to the right angle. So once we have that set up, we can just plug in, do our cross products. So 7.25x equals 182.25. Divide both sides by 7.25. And we have x equals 25.1. And the problem asks the length of the rod, so we need to add that 7.25 to that. So we get a total length of we're going to get about, this is with rounding, because when I did that division it isn't perfect, but it's about 32.39 rounding to the nearest hundredth. And I should have labeled that inches. Here's that familiar diagram again. If the altitude is drawn from the vertex of a right angle of a right triangle to its hypotenuse, familiar, then the measure of the leg of the triangle is the geometric mean between the measures of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So looking at our little small triangles again with our arcs marked, we can see they did XZ is the hypotenuse in the big triangle, is to XY is the leg adjacent to the 1 arc angle as XY, so that's the hypotenuse in that triangle, is to XW, the leg adjacent to the 1 arc angle there. And then again, same relationship, XZ is still the hypotenuse in the big triangle, is to YZ, the other leg, the one adjacent to the 2 arc angle there in my drawing, as YZ, the hypotenuse in the smaller triangle, is to WZ, the side adjacent to the 2 arc angle of the smaller triangle. So in example 4, they ask us to find C and D in triangle JKL. So because we've got a right triangle with an altitude drawn, KM is the altitude. It's drawn from the vertex and it's perpendicular to the opposite side. So we can use theorem 7.2. So JM is to KM as KM is to LM, which the setup is the tricky part. Solving's easy. So we have 100 equals 5C. So C is 20. So to solve for D, we could use theorem 7.3, which says that the measure of the leg, so in this case JK, of the triangle is the geometric mean between the measures of the hypotenuse, so JL, and the segment of the hypotenuse adjacent to that leg, so JM. So we wrote the proportion JL is to JK as JK is to JM, and then all we have to do is put in the numbers that go with that. JL, well, we know C is 20 now, so JL will be 25 is to JK, which is what we're trying to find. Oh, that's a terrible D. As JK is to JM is the adjacent side is 5. And then cross product, so 125 equals D squared. Take the square root of both sides, and the square root of 125 we could simplify to 5 squared of 25. And I know what the square root of 5 is, or sorry, the square root of 25 is 5. I'm getting ahead of myself. So it simplifies down to exactly 5 square root of 5. And if you use the approximate button on the calculator, that'll be about 11.2, rounding to the nearest tenth. All of our hard work is summed up in 2 sentences. The geometric mean of 2 numbers is the square root of their product, and you can use the geometric mean to find the altitude of a right triangle.